Application of Surds to Trigonometrical Ratios and Graphs. A comprehensive exploration of how surds apply to trigonometric ratios, and an introduction to sine and cosine graphs. Understanding trigonometric ratios in surd form. Trigonometric ratios can be expressed in surd form, providing exact values rather than decimal approximations. We'll explore how to find the sine, cosine, and tangent of specific angles, 30 degrees, 45 degrees, and 60 degrees, using geometric principles. Trigonometric ratios of 30 degrees and 60 degrees. We start with an equilateral triangle of side 2 units, and divide it into two right triangles. By drawing a perpendicular from A to BC, we create a right triangle that allows us to calculate the exact values using the Pythagorean theorem. Deriving the 30 degrees and 60 degrees ratios. Applying Pythagoras. 2 squared equals to 1 squared plus x squared. This is derived by applying the Pythagoras theorem in a right-angled triangle, with hypotenuse 2, one leg equal to 1, and the other leg equal to x. 4 minus 1 equals to x squared. This results from subtracting 1 squared from both sides. X equals to square root of 3. This is simplified by taking the square root of both sides. For 30 degrees, sine of 30 degrees equals to 1 divided by 2. This is derived as the ratio of the side opposite to 30 degrees over the hypotenuse. Cosine of 30 degrees equals to square root of 3 divided by 2. This is obtained as the ratio of the side adjacent to 30 degrees over the hypotenuse. Tangent of 30 degrees equals to 1 divided by square root of 3. This follows from the ratio of the side opposite to 30 degrees over the side adjacent to 30 degrees. For 60 degrees, sine of 60 degrees equals to square root of 3 divided by 2. This is obtained as the ratio of the side opposite to 60 degrees over the hypotenuse. Cosine of 60 degrees equals to 1 divided by 2. This is derived as the ratio of the side adjacent to 60 degrees over the hypotenuse. Tangent of 60 degrees equals to square root of 3. This results from the ratio of the side opposite to 60 degrees over the side adjacent to 60 degrees. Trigonometric ratios of 45 degrees. For 45 degrees we use a right-angled isosceles triangle. Applying Pythagoras, m squared equals 1 squared plus 1 squared. This simplifies to m squared equals 2. Therefore m equals the square root of 2. For 45 degrees, sine 45 degrees equals 1 over square root of 2. This is simplified to square root of 2 over 2. Cosine 45 degrees equals 1 over square root of 2. This is simplified to square root of 2 over 2. Tangent 45 degrees equals 1. Summary of special angle ratios. Observe the table to analyze the angle values for sine theta, cosine theta, and tangent theta at 30 degrees, 45 degrees, and 60 degrees. For 30 degrees, sine 30 degrees equals 1/2, cosine 30 degrees equals square root of 3 over 2. Tangent 30 degrees equals 1 over square root of 3. For 45 degrees, sine 45 degrees equals square root of 2 over 2. Cosine 45 degrees equals square root of 2 over 2. Tangent 45 degrees equals 1. For 60 degrees, sine 60 degrees equals square root of 3 over 2. Cosine 60 degrees equals 1/2. Tangent 60 degrees equals square root of 3. These exact values are crucial for solving problems without approximation errors. Practical example. Finding unknown lengths. Finding x using tangent 60 degrees. Tangent 60 degrees equals x over 3. This is simplified to square root of 3 equals x over 3. Therefore, x equals 3 times square root of 3 centimeters. Finding z using cosine 60 degrees. Cosine 60 degrees equals 3 over z. This is simplified to 1/2 equals 3 over z. Therefore z equals 6 centimeters. Finding y using sine 30 degrees. Sine 30 degrees equals y over x. This is simplified to 1/2 equals y over 3 square root of 3. Therefore y equals 6 square root of 3 centimeters. Another example. Finding unknown lengths. This problem asks us to calculate BC, the length of side BC, CD, the length of side CD, AD, the length of side AD. We would apply the same principles of trigonometric ratios in surd form to find these unknown lengths. Introduction to Trigonometric Graphs. sine and cosine graphs. Now we'll explore the graphical representation of sine and cosine functions for angles between 0 degrees and 360 degrees. These graphs help us visualize the cyclical nature of trigonometric functions and solve equations. Developing sine and cosine graphs from the unit circle. The sine graph and the cosine graph are both developed using the unit circle, which has a radius equal to 1 unit. As a point P moves around the circle, its position is described by an angle theta measured from the positive x-axis. The x-coordinate of point P corresponds to the cosine of theta. This means that the horizontal distance from the center to the point gives the cosine value. The y-coordinate of point P corresponds to the sine of theta. This means that the vertical distance from the center to the point gives the sine value. By plotting these cosine values and sine values against the angle theta, we generate the characteristic wave-like curves of the cosine function and the sine function. Key properties of sine and cosine graphs. Range. All values of sine theta and cos theta lie between +1 and -1. Wave shape. Both curves have the same wave shape, but start from different points. Sine A starts from 0. Cosine starts from 1. Symmetry. Each curve is symmetrical about its crest, high point, and trough, low point. Multiple solutions. For most values of sine theta and cos theta, there are usually two corresponding values of theta between 0 degrees and 360 degrees, except at quarter turns. Values at quarter turns. These key points help us sketch the graphs and understand their behavior at critical angles. Observe the table values for 30 seconds before we move along. Graphing exercise. Sine function. Instructions. We are asked to complete a table of values for sine of theta, where theta takes values from 0 degrees up to 360 degrees in steps of 12 degrees. Each sine value should be found using tables and written correct to 2 decimal places. Graphing parameters. On the horizontal axis, which represents theta, the scale is 2 centimeters to 60 degrees. On the vertical axis, which represents sine of theta, the scale is 10 centimeters to 1 unit. Purpose. This exercise allows us to plot points accurately, and then join them smoothly to obtain the sine curve. It shows how the values of sine of theta rise from 0 to 1, then fall back through 0 to -1, and finally return to 0, as theta completes the cycle from 0 degrees to 360 degrees. Through this plotting, we gain a deeper understanding of the periodic nature of trigonometric functions, and how they repeat in cycles. Graphing complex trigonometric functions. Y equals sine 2 theta minus cosine theta, for theta between 0 degrees and 180 degrees. Prepare a table of values. Use scale, 2 cm to 30 degrees, horizontal, and 5 cm to 1 unit, vertical. Draw the graph. Find solutions to sine 2 theta, cos theta equals 0. Determine the maximum value of y. Solving trigonometric equations graphically. Graphs allow us to solve trigonometric equations visually. Plot the function. Draw the graph of the trigonometric function. Identify the target value. Draw a horizontal line at the value you're setting the function equal to. Find intersections. The x-coordinates of intersection points are the solutions to your equation. Finding maximum and minimum values. Graphs also help us identify extrema, maximum and minimum values of trigonometric functions. The highest point on the graph gives the maximum value. The lowest point gives the minimum value. The x-coordinate tells us where these extrema occur. Exercise Part 1. Graph y equals 1 plus cosine of 2x. This means we are asked to draw the curve defined by the function y equals 1 plus cosine of 2x. The +1 shifts the cosine graph upwards by 1 unit. The 2x inside the cosine makes the curve complete 2 full cycles between 0 degrees and 360 degrees. For 0 degrees, less than or equal to theta, less than or equal to 360 degrees at intervals of 30 degrees. This tells us that the values of theta should be taken starting from 0 degrees, then 30 degrees, 60 degrees, 90 degrees, and so on, until 360 degrees. Each step increases by 30 degrees. Use scales, 2 cm to 30 degrees on the horizontal axis. This means every step of 30 degrees along the horizontal axis should be marked as a distance of 2 cm on the graph paper, 2 cm to 1 unit on the vertical axis. This means every increase of 1 unit in y should be represented by 2 cm along the vertical axis. Solve equation. This instruction tells us to find the values of x that satisfy the given equation, using the graph we will draw. Use your graph to solve. Y equals 1 plus cosine of 2x equals 0. This means we need to locate the points where the curve of y equals 1 plus cosine of 2x crosses the horizontal axis. At those points, the value of y is equal to 0, and those x values are the required solutions. Exercise, Part 2. Draw the graph of sine 3 theta for values of theta from 0 degrees to 360 degrees using appropriate scales. Create a table of values. Calculate sine 3 theta for values of theta from 0 degrees to 360 degrees at regular intervals. Choose appropriate scales. Select scales that will clearly show the complete cycle of the function. Plot points and connect. Plot each point and connect with a smooth curve. Label key features. Mark maximum/minimum points and zeros of the function. Key differences: the sine of theta versus the sine of 3 theta. The sine of theta. The graph of sine of theta completes one full cycle when theta increases from 0 degrees up to 360 degrees. This is because the standard sine curve repeats every 360 degrees. The period of sine of theta is 360 degrees. This follows from the fact that sine of theta returns to its starting value after 360 degrees. The key values are reached at theta equal to 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. These points mark the maximum, minimum, and zero crossings of the basic sine wave. Sine of 3 theta. The graph of sine of 3 theta completes 3 full cycles when theta increases from 0 degrees up to 360 degrees. This results from multiplying the angle by 3, which causes the wave to oscillate 3 times faster. The period of sine of 3 theta is 120 degrees. This is derived because dividing the usual period of 360 degrees by the factor 3 gives 120 degrees. The key values occur 3 times as frequently as those of sine of theta. This follows from the shorter period, meaning the curve reaches zeros, peaks, and troughs more often within the same range. Summary: trigonometric ratios and graphs. Exact values. We can express trigonometric ratios in exact surd form for special angles: 30 degrees, 45 degrees, 60 degrees. Practical applications. These exact values help solve geometric problems with precision. Graphical representation. Sine and cosine graphs visualize the periodic nature of trigonometric functions. Problem solving. Graphs enable us to solve equations and find maximum/minimum values.